counting and distinct elements.
Okay. Good morning, everyone. First, thanks a lot to the organizers for the invite. So, I want to discuss yet another place where circuits can meet, and there are very interesting things to do. So, the talk is about two problems. One is the problem we have been looking at since morning, model counting. And there's another problem called distinct elements. It's a fairly fundamental problem in streaming. It's been studied for a long time. And the work is joint work with three of my collaborators who work in streaming, Arnab Bhattacharya, Pawan Aduri, and Anvi Vinodchandran. And we kind of realized that these two communities, they have been developing similar algorithms for nearly 40 years. And there can be a lot achieved by if we try to translate algorithms in one community to another community. Okay, so that with that as the backdrop. Right, so let me first quickly model counting problem we have seen so far. We have a set of Boolean variables. There's a formula of these Boolean variables. The problem is to count how many satisfying assignments there are. I'll use the notation sol of phi to denote the set of satisfying assignments of this formula. Okay. If you have a formula that is x1 or x2, there are three satisfying assignments. All the assignments except where we assign x1 and x2 to 0, 0. And a counter should be able to give an answer 3. Okay. This problem is typically sharply hard. Even the approximation of it is NP-hard under mild restrictions to the formula. So a lot of work that has happened for nearly 40 years now. The approximation of this was initiated by Stockmeyer in his seminal work in 1983. And the focus on algorithmic development says, well, if it's going to be NP-hard, we are going to use NP oracles, which are set solvers in practice. So we would like to design algorithms that don't make many calls to these NP oracles. And there's a lot of focus on also trying to come up with algorithms that make nicer kind of calls to the set, the set solvers in practice. So the concern here is that, well, we would like to optimize the number of NP queries to make. Okay, it's NP-hard. We will have to make some queries, but we would like to optimize the number of queries. And I'm going to now look at the approximate variant is to be able to compute an answer which is within 1 plus epsilon factor with confidence at least 1 minus delta. So epsilon and delta are the two parameters. So this is the approximate variant of the problem we are looking at. This is still NP-hard for lots of simple variants of the problem like monotone CNF, two monotone CNF, and so on. The other problem is from a very different community, which is streaming. So here is how to think about this problem. On your website, it's nice to have a small counter that can tell how many unique visitors have visited your website. So a lot of people visit your website. Some people check your website very frequently, so you don't want to update the counter every time somebody is visiting again and again. So in this case, you have a stream of elements that come in, and we would like to be able to compute how many unique elements, distinct elements you see. This is also known as, you can think about a frequency vector, and this becomes the zeroth frequency estimation. So a popular name for this problem is F0 estimation. Here's a simple example. We have a stream, and you see 1 and 2 are repeating very often, while 5 comes only once. But at the end of the stream, we would like to count how many unique elements we have seen, and the elements we have seen are 1, 2, 3, 5. Okay, the number is 4 here. Again, this turns out to be a very well-studied problem in the community. If you really want to count the number exactly, there's not much you can do. So we again focus on epsilon delta approximation. And here, there's a very simple solution. You can try to store all the elements you see. We have a big hash table, but then your hash table will be of the same size of the 2 to the n. So the focus is on having smaller space complexity. Okay, so one would like to store as few bits as possible. So as I told you, these two problems have been very well studied. There are communities that have been working on independently for a long time. In fact, the first work on both of these problems happened about at the same time in 1983 and 1985. Recently, I found out that the first work really happened in 1983. So the same year, these two communities start studying these problems, and for next 35, 40 years, they have been building techniques independently. And since all of this work started with a chance meeting, and we were just trying to tell each other what we are working on, and we realized that we kind of have similar set of arguments. In particular, we rely on these two-wise independent hash functions. So let me introduce you this notion of two-wise independent hash functions. So we have hash function that map from 0, 1 to the n to 0, 1 to m. So the cells that can be represented by m bits. What two-wise independence says that if you take any two elements in the domain and take any two cells that we are mapping to, the probability that such a function h randomly chosen maps y1 to alpha1 is same as h maps y2 to alpha2, which is 1 over the number of cells. And they are pairwise independent. So the probability h maps y1 to alpha1 and h maps y2 to alpha2 is product of marginals. Where are these two-wise independent hash function? I'll just show you a standard construction. A set of variables. If you want to construct a hash function, we choose m random XORs. XORs are addition modulo 2. The way we choose these XORs is we pick every variable with probability half and we XOR them together. If you had to choose any of the cell, then it's really setting these XORs to 0 or 1 randomly and independently. And now this choice of a cell, all of this can be represented by, such a hash function h of x equals to alpha can be represented by ax equals to b, where the operations are over Galois field 2. All right, so this is kind of all the characters we need. There are two problems. There is a central concept which has been around for a long time. So now I'm going to tell you the state-of-art algorithm for approximate counting. Okay, here is how the algorithm works. Well, you have access to, a lot of this work is motivated by set solvers in practice. So a set solver can enumerate solutions, but of course, we can't enumerate exponentially many solutions. So it would be nice if we go and say, well, do we have more than some threshold many solutions? We can enumerate those many. If the answer is no, we would like to partition the solution space. And this is precisely where we can use a pairwise independent hash function, an XOR. We pick one of the cell, we ask the same question, is the number of solutions greater than threshold? Again, it turns out if we have more than threshold many solutions, we partition further. We keep doing it until we reach a point where the number of solutions is indeed less than threshold. And at that point, our estimate is the number of solutions in this cell times the total number of cells. So that's kind of the high-level approach. And there's a lot of work on how you want to do the search and so on. But this is the approach. We use it XORs, which is repeatedly partitioned further until we reach a point where the number of solutions is less than threshold. Those we can enumerate all of them, and then we can estimate. I think it would be good if you ask any questions as we go along, because finally I'll just tell you everything and then I'll show that, well, these were always connected. So these two communities could have talked to each other 40 years ago. Okay. All right. So now let me tell you one of the state-of-art algorithm for distinct elements. The idea for distinct elements is, think about you are throwing balls, which is kind of how you can always think about hash functions, right? This is balls and bins. So you are throwing balls on this line. And if you just throw one ball, then what's the expected position for this ball to fall in? Halfway, right? There are no trick questions here. It's supposed to be a talk before lunch, so Right. So if you have many balls, if you keep throwing, then some will fall on this side, some will fall on that side. But if you throw lots of balls, then there will be chance that there will be some ball that falls as close as possible to the left side, right? One. We can try to formulate this idea. We can say that if there are many balls, you throw them, then the number of balls you throw is proportional to the smallest value of the left side position ball. If you throw many balls, they will get closer and closer to 1. So the inverse is a good proportionality. We can try throwing balls, but this should work out. Okay, so we can come up with an algorithm for it. We take a hash function. We are just going to keep track of the minimum hash value. So every time an element comes in, we figure out what's the minimum hash value, and we just keep track of the minimum hash value. And at the end, the estimate is 1 over the minimum hash value. So again, we had to only keep track of about n bits instead of keeping track of 2 to the n things, right? The hash value is just an n bit. Yeah.
If it's this simple, what were those 20 papers all about?
Of course, there's a lot that goes in. Is how you prove the 1 over epsilon square guarantees and the hash functions, and then the much more complicated variants of this. The high level idea is simple, but all right. So well, now I would like to tell you that how these algorithms developed for these two communities can be transformed one to the other. And the recipe is again going to be very simple. So for that to start with, let me tell you, almost all the algorithms that have been developed for the sketching, for the distinct elements, they are usually called sketching algorithms, just the name in the community. And the way these algorithms work is in the following template. You choose hash functions, just the way we did right now. We are maintaining the smallest hash value, so that's a sketch. Every time an element comes in, we process the element. Kind of makes sense, we should do it. What does processing means? We update our sketch. And at the end of the stream, we compute our estimate based on the sketch we have. I showed you one example, which is to keep track of the minimum value. Later on, I'll show you another algorithm, but there are many of this type. You have some sketch, you update the sketch. Finally, you compute the count just based on the sketch. Okay, so there is kind of a one paragraph paper that we wrote and one slide summary. How we can think about is if we want to take these algorithms, let me just introduce one more notation. So given a stream, I'll use AU as the set of unique elements in the stream, the distinct elements. So we want to take an algorithm that has been developed for distinct elements and transform into a model counting algorithm. So what we think about is we can view a formula as a symbolic representation of its. So it is, of course, a symbolic representation of its solutions, and that is captured by a set. Okay. So we can take an algorithm and we can ask, well, what is the property between the sketch, the hash functions we have, and the set AU, the set of distinct elements in the stream? I mean, there is some property. There's an algorithm after all. We want to formalize what's the property between the sketch, the set of hash functions, and the set AU, the set of distinct elements. So we'll formalize this property. It has to lie in some language. And now, because the existing algorithm is correct and it computes the count estimate just based on the sketch. So given a formula phi, again, we can choose these hash functions randomly, can we come up with an algorithm that could construct the sketch so that the same property between the sketch, the hash functions, and the set of solutions of the formula holds true? From rest of the correctness argument, it must be the case that given the sketch, we should be able to estimate the cardinality of the sets of solutions of the formula. Remember, the number of distinct elements is really the cardinality of this set AU, the set of distinct elements. So if we can construct such a sketch, we get an algorithm.
Can you repeat what the sketch is?
Yeah, so let's try to apply to this one algorithm we saw. So the sketch here was really just the smallest hash value. A simple algorithm, we were keeping track of the smallest hash value. So let's try to capture what was the relationship between the sketch, the hash functions, and the set AU. Well, it was really the sketch was the smallest hash value. Okay? It's not going back. You have been agreeing with me so far. All right. So, well, we are just going to replace AU with sol of phi. So now it would be nice if we could compute the smallest hash value over the set of solutions of this formula. Of course, there is a simple way, which is to enumerate over all the solutions, but it's an optimization problem. You don't have to really go over all the solutions of the formula to compute the smallest hash value. In fact, you can do, this is a classical max set problem. You do many calls to the NP oracle. You can guess. You can say, yeah, I think the smallest value is this. Can you find a solution that's less than this? And you continue to do a set of NP calls. So given a formula and set of these hash functions, we can come up with a sketch such that this property holds. And we can do that by just making polynomially many NP calls. So there is your one approximate counting algorithm. Take a formula, choose hash functions randomly, compute the smallest hash value.
How do you solve with that the questions of whether there is a smaller hash?
I mean, first in theory, you can just say, yeah, does there exist an element such that h of x is less than some value? Does there exist an assignment so that the hash, because hash is a matrix that you can compute? In practice, it's of course a good idea to go bit by bit, because you have a number, you say, does there exist something that goes? Yeah. So in theory, you just say, does there exist? In practice, you should do.
So here you have a sampler in the set of solutions of.
No.
What is the stream of elements here?
So that's we are transforming into a model counting algorithm. So given a formula, we want to count the number of models of this formula. So we would like to construct a sketch, which is the minimum hash value over the solutions of this formula. Right? So you ask, well, given this hash function, does there exist a solution whose hash value is midway, right? And then you do a binary search. So now let's use this recipe for another algorithm. So I'll tell you another algorithm. This turns out to be the most efficient algorithm. Well, variant of this is the most efficient algorithm if you want to be able to have the smallest space complexity. Okay. In streaming, one cares about space complexity. So this is called bucketing algorithm. That's the name in the community. Here's how it goes. We choose a hash function. We are going to maintain what's called the level, and there's a bucket. Okay, this is our sketch, level and bucket. The way we do is that every time an element comes in, we check if the last L bits are all 0. If that's the case, then we add the element to the bucket. We don't want to store too many things, so at any point the number of elements in the bucket is greater than some threshold, which is 1 over epsilon square. We increase the level. And we filter out all the elements whose last L, now L is L plus 1. So we check for all those current elements. If their last L bits are L plus 1 bits are not 0, you remove them. This is the, and at the end, what we do is our estimate is the number of size of this bucket times 2 to the L. That's our estimate. So given the bucket and L, we can make this estimate.
Question. Is that still pairwise independence that you need here?
Yeah.
You don't need to go beyond that.
We don't need to go. So of course, that was a lot of work in showing that pairwise independence suffices. Well, I told you that you can think about these hash functions using XOR. So what is really, every time we want to add the elements to a bucket, it's really the element that satisfies the current set of XORs. And every time we have to increase the level, it's really add another XOR. Okay. So let's now use our recipe, take this algorithm and come up with a new model counting algorithm. The first step of our recipe is to figure out what is this property between the sketch, the set of hash functions, and the set AU. Well, it's really the algorithm at the end of the stream. What does it do? It contains the bucket. So the bucket has all the elements whose last L bits are 0. And the level that with which we end the algorithm is that if you were to have the level L minus 1, then we would have more than threshold many elements. That's the reason we increase the value of L. This is what we did. We increase the value of L every time we reach threshold. So it's really L is the first value where the number of elements is less than threshold. We can again replace AU with solve phi. So it would be nice to come up with a sketch where you have the level and the bucket, so that the bucket has all the solutions of this formula. If the level was supposed to be L minus 1, then you will have more than threshold many solutions. So given a formula, can we come up with an algorithm that can reconstruct such a sketch? Turns out, yeah, you can again do polynomially many NP calls. Actually, this is the algorithm that I started with. This is the model counting algorithm that I started with. So it turns out you can use this recipe for lots of all the work that has gone on in streaming, and you immediately get a lot of new counting algorithms. Community has focused on one. We understand its performance. There is much more to do. Okay, so now what are other things we can say by this connection? Well, there are some interesting things. One is if the construction of this sketch is in polynomial time, then there's an FP-RAS for the corresponding class of formulas. So for example, DNF, union of XORs, the sketch can be constructed in polynomial time. Immediately you get an FP-RAS.
Yeah. So if I remember correctly, in the only Martin sketch, is this scaling factor. You didn't show it here. Is that?
Yeah. So corresponding to Flageolet-Martin, you get another algorithm. So there are lots of algorithms that have been developed. So for every such algorithm in the streaming, there's a corresponding counting algorithm.
Okay. So including the one that make use of continuous Gaussian variables.
Well, there it gets tricky that how there's an algorithm. It's not. What's not clear is whether you can do it in the polynomially many calls and theory. So now it also turns out that you can say something more interesting about this two areas. So if there are this polynomial space algorithm in streaming for distinct element counting, that implies a bound on the number of queries you make in counting. Why so? Because if you think about streaming, if you are storing something, it's because we can't really recompute based on what we already have. That's the reason we had to store some bits. So in case of counting, those bits will have to be queried from the oracle. If we could just recompute based on what we have, we wouldn't call a oracle. It turns out for all the non-algorithm we discuss in our work, we can show that Pn polynomial in n, or some polynomial, we get the same bound for the NP queries. But a black box result is quadratic, so there's a gap that I hope someone takes up and reduces this gap. It also, you can go the other way. You can look at, there is a lot of work in distributed streaming. There are lower bounds on how much space is required, and that results to lower bounds for some of the DNF counting settings, where the distributed makes much more sense. So immediately there is a lot of these results you can lift in a very black box manner the moment you realize these are really two same problems. Okay, so let me now complete, since I have 2 more minutes. So the second part has to be even more simpler. Can we go from counting to streaming? Okay. Okay, so first is the algorithm that I started with for counting that also turns out to have an FPRAS for DNF. So if you start with the DNF formula, you get an FPRAS. FPRAS is fully polynomial randomized approximation scheme. Okay, so, well, what is a stream after all? You get elements, and finally we wanted to compute the union of elements we see and then the count distinct elements we see, right? Union in logic is just disjunction. So a stream, if you think about, every element can be represented by a term. Counting the number of elements we see is just doing a counting of the DNF. So if you have an algorithm over DNF that has an FPRAS, which can process one term at a time, it immediately gives you an algorithm for streaming. In fact, the moment we see make this observation, then in case of streaming, there was a lot of work on the structured sets, where essentially you don't just get an element, but you get a set of elements like an interval. There's fairly complicated techniques, lot of work, involved technical work that was done. But the thing is that for every element, if you can represent a DNF formula, you get an immediate streaming algorithm. So there are lots of models. It's just all of that. All of those results can be one can derive just by saying, well, all of this, there's a small DNF representation for this set, and disjunction of DNF is still DNF. So yeah, one particular case is, well, instead of an element, you get intervals, and you want to compute the union of intervals. So every interval is a small DNF. Union of DNF is DNF. The algorithm works.
So I'm lost about your assertion that the number of solutions is equal to the cardinality of the union of the AIs. Why is that the case?
Because let's just consider the case where each of these is an element. So let's say we have 4 bits. In particular, I want to say all the numbers are, so we get elements that look like 1, 5, 3, 7, 3 bits. So 1 is really 0, 0, 1 if I look at the binary representation of these numbers. Each of them I can encode as a DNF by saying Now if I do the union of this, it's just really the number of, because for every term I'm writing a DNF, for every element I'm writing a DNF term. And now you can see that for an interval, I can just come up with a DNF formula for an interval. Don't need any complicated algorithm. Right. So let me conclude. I talked about that. Well, it's really interesting when we looked at these two communities have never cited each other and have developed the optimal algorithm in both communities turn out to be the same. So I talked about how we can reduce transform algorithm from streaming to counting and vice versa. There are lots of interesting things to do here. We certainly have a lot of algorithms. We don't know their performance in practice in the field of counting. But I think what I'm much more excited about is that, well, between this formulation of circuits and streaming, are there other problems that share similar connections? For example, entropy is a very well-studied problem in the context of streaming. What does it imply for calculations of entropy or probabilistic circuits and so on? There are lots of other problems, like higher moments is a very important thing, heavy hitters and all. What are those connections and what are those concepts in the context of distinct circuits? So there's much more to do. We have barely started here. So with that, I'll conclude. Thanks for being a wonderful audience.
Questions?
Thank you, Kuldeep. It was a very nice talk. It's a bit of a far-fetched question, but knowing you, I guess you have thought about it already, but you can just say me that you haven't tried. So you showed us a way of approximating the number of solutions of a CNF formula by having this NP oracle call, where you basically look for the smallest solution with the smallest hash. What happens if your formula is encoded as a structured DNNF, for example? I know that Marcello will be talking about something related, but I was wondering whether your technique could give FPRAS directly for structured DNNF.
Yeah, we thought a bit. I mean, I don't know.
Okay.
Yeah.
Thanks.
I don't know.
We can.
But I really don't know, so it's not like something in submission or so.
Other questions?
What do you mean with the higher moments here?
So there is a lot of work in streaming. In fact, there's another program going on where, so instead of, you get a stream of elements and you say, well, so one way to think about all this, we have a stream of elements. So for every element in the domain, I can talk about what's the frequency for each of the elements. And what's the zeroth frequency is really the so when p is equal to 0, it's really all the elements whose frequency is non-zero. That's what we did. When p is 1, it's the length of the stream. When p is 2, it becomes what's very well studied in what's called heavy hitters. So the weightage of elements that occur more often carry more weightage, but this is called second moment. You can ask the question for 3, 4, 5, 6. There's a lot of work that have been developed over the years. I also think there's another line of work that can be very interesting in streaming. I talked about one model of streaming, which is insertion model, where you only insert, but there are models where you delete, turnstile model, and so on. It would be interesting what is the kind of analog in the circuits, because for all these models, there's a lot of work. There are very nice algorithms developed. If you understand what's the analog in circuits, you immediately get algorithms by kind of, I hope we get algorithms by following the kind of recipe here, is that you can always think of a streaming algorithm just operating over this property sketch and so on.
Thank you, Kuldeep. I'm confused about the following. What do you really mean by connections or relationship between these different problems? Let me explain. the counting problem, we understand the worst case complexity, Sharpie complete. But distinct elements is a trivial algorithm, right? I maintain a list of different elements. So it's not a question of reducing one hard problem to another hard problem, but it's another kind of connection. What is a precise statement or abstract content of this?
Yeah, so I think, so really so first I should thank Fokyan for pushing us to get this result. He asked us a similar question 2 years ago and we got it. So really the connection that we are, I think in streaming, one cares about the space complexity. And
So access to the disk. Right?
Yeah.
Or number of
the storage. And in case of counting, or I want to just broadly sketch in case of circuits, we often care about the query complexity or the time complexity. So the connections are going to be between the space complexity in those in case of streaming to the time complexity in case of counting. So see here we are talking about the space complexity in streaming implies the time complexity in.
Okay, so it's a trade-off between one resource in one problem and another resource in another problem.
Yes.
And that's what you are asking at the end about
other problems, yeah. And to me, it's when you see that the two communities for it's also very parallel work. If you look at the work happening, even the papers are within 2-3 years of each other, and they would end up with the same optimal algorithm, because one was focused on space and another on time, but it's really kind of the problems are really inherently same at some point, that the two communities would end up with the same ideas.
Here it's not exponential space, it's logical.
Yeah, it's so our we were looking at n bits, so this is polynomial in n bits. So this is really exactly for distinct elements. There's a trivial algorithm for exponential space. There's a trivial algorithm for exponential number of queries.
Okay.
So maybe, yeah, thanks for a very nice talk. So playing on your practicality question at the end. So in practice, F0 estimation is typically done by like hyperlog or something like that. Now, is there a corresponding version of hyperlog in model counting?
We know the recipe immediately gives, but I haven't had time to experiment and see whether it works really well in practice. And there's an immediate, in hyperlog, you are computing some bits. You can ask over the space of the formulas, I want to compute those bits. So there's an immediate analog by following the recipe, but I don't know the practical performance.
All right. Thanks, Kuldeep, again.
Thank you.
So now we break for lunch and we return at 2 p.m. See you.